show you probably on Thursday. This is fairly complex material on the linkage. So I am going to go around that for the moment and jump down here. So more of an overview of genetics. We have our set of chromosomes. The basic set of chromosomes everybody gets includes 22 pairs of autosomes. Those are all the chromosomes with numbers on them. And those are basically arranged from biggest to smallest. I think 21 is actually the smallest, but approximately the smallest down there. So we're going from the biggest to the smallest chromosomes in descending order. And these are the chromosomes where everybody gets one from each parent. And then you get to the sex chromosomes. And that's where we get the, of course, obvious male-female difference. So XX for female, XY for male. There are other species that do this differently. There are other ways to get sex determination. But one thing with the fruit flies is they do it the same as us. They have the same arrangement, and so that's been very important for us in genetics. Fruit flies have made an excellent model organism. If you wanted to study inheritance in people and do a controlled experiment, you'd have to be keeping a bunch of humans captive in the first place, and then controlling who mates with whom. I mean, it would be a monstrous thing to do. But then you'd have to wait 20 years to get results for a generation. Fruit flies, we can do that, and it only takes a week to get results. They breed so fast, and no one gets upset if you're keeping some fruit flies in a jar, right? So fruit flies have been an excellent model organism in the same way that you do with things like lab mice. So we'll come back to the fruit fly part a little bit later. Thing with them, again, is their sex determination works the same as with us, and that's been very important with some of the genetic studies. So if you have a gene that's being passed on that is on one of the autosomes, and you're looking at a dominant effect, let's say of a mutated gene. Imagine we have a harmful version of a gene that's rare in the population, but this father has it. He has one of these rare mutant versions and one normal version. In the case of a dominantly inherited disease, it only takes one copy of that to cause a disease. But we do have some conditions that are like that, where most people are actually recessive. But here and there will be a person out there who is like this, and in that case, dad there will pass this mutated version of the gene on to half of his kids. So you get some conditions that are like that. And in that case, there's basically no skipping of generations involved. With a dominant mode of inheritance, generally that trait is going to show up in every generation. And you'll get it just by having one copy of a mutated version of the gene. And that's the case with, for instance, these guys. Anybody recognize the one in the middle? Mm-hmm. Yeah, he unfortunately died recently, but it was in the Austin Powers movies, of course, Mini-Me. And that is an example of a dominant type of autosomal condition. The most common kind of dwarfism, achondroplasia, which all three of those guys have, it only takes inheritance of one mutated version of that gene, mutated in a particular way, to cause this condition. But there are other kinds of diseases that happen too. Fatal familial insomnia is one. It's luckily very rare, but that is a fatal brain deterioration, starting usually when the person is already in his or her 40s, and the first onset, the first symptoms, you start having trouble sleeping, and then your brain deteriorates and you die. Imagine that you are getting into your 40s and you already know that your dad died from that, and you're just waiting to see if it's going to be your turn, and then you're in your 40s and you start having trouble sleeping. What does that do to a person? Pretty awful. Huntington disease is a similar thing. Again, a fatal brain deterioration, dominantly inherited. So all you have to do is inherit it from one parent who actually has the disease. Certain other things work the same way. What happens is you're inheriting one normal allele for a gene, and one mutant one. And the mutant one is making some sort of harmful version of a protein. It's effectively working as a poison. In the case of the achondroplasia, you won't even survive at all if you have two of the mutant ones. These guys are all heterozygotes, one normal and one mutant version of the gene. It's affecting formation of cartilage. And somebody who actually is produced by mating, let's say of two dwarfs that are both heterozygous, and if there is a fetus developing that has two of the mutant versions of the gene, it'll lead to a self-abortion, a miscarriage. So you won't even make it out of the womb alive unless you have at least one normal version of that gene. A lot of disorders, though, are passed on in an autosomal recessive manner, and that's what happens here. And it's also the same with the sickle cell and with the cystic fibrosis, where parents can be carriers. They'll have one normal and one mutant version, and the only way to actually get the full-blown disease is if you get the mutant gene from both parents. In that case, there's 1 out of 4 that come out that way. Now let me ask you, imagine you have a family. Say there's a girl who has cystic fibrosis, which is following this mode of inheritance. Her parents are normal, her brother seems normal. What are the odds that her brother is a carrier? Is it 2 out of 4? Is it? It's 2 out of 3. If you're in a family and we know that the parents must be carriers because this girl already has the disease, then her brother can't be that one at all. He's got normal health, but he could be one of these, and 2 of those say that he has the allele. So the odds are actually 2/3. If you're taking a genetics class later, say like a 300 level genetics class, they will often give you conditional statements like, assuming this, you already know this particular thing. Now, what are the odds? That's what I just gave you there. I already identified for you that we have this little a allele in both parents, and yet the brother doesn't have the disease. What does that mean about the odds of him being a carrier? But in this case, you can have a disease condition hiding, skipping generations. Now, let's say these parents have children and their first child has the disease. What are the odds then, if that already happened, what are the odds that their second child will have the disease? Did they basically use up that chance and they don't have to worry about it anymore? No. Again, it's 1 out of 4. Every time it's 1 out of 4. So here's several examples of diseases that follow that mode. Cystic fibrosis would be one. I didn't put it up here. The Tay-Sachs is another fatal kind of a thing that shows up in some children. Same for this one. Maple syrup urine disease. Sounds kind of funny, but it's not. That leads to death as well. Werner's syndrome is one of the ones causing very accelerated aging. You don't want any of these. And what is happening with those is that you're inheriting genes that give you faulty information for making a protein. The protein that you're making doesn't do a job correctly. It's not poison, but there is a particular job that needs to be done, and it's not getting done. So if you inherit 2 of these corrupted versions, then you have some sort of metabolic error that's going on, which can lead to early death in some cases. Very often, if a person has one normal and one mutant version of the gene, the normal version gives them enough good versions of the protein to have normal health. That's what happens with cystic fibrosis, also with sickle cell. You have, if you're heterozygous with sickle cell, you basically have enough normal hemoglobin that your red blood cells keep the right shape. But there is a subtle change which makes it hard for malaria to get a foothold in a person. So if you're in a malarial environment, that's the best way to be a heterozygote. Does that give any advantage to people here who are, say, carrying the sickle cell allele? No. We used to have malaria, but we got rid of it. So in past times and other places, it can be good to have that sickle cell allele, but not here. So I think that's where we'll stop.